these very nice compounds. In this talk, I'll try to explain the main ideas of a method I developed during the last years. The method, as the talk said, is a semi-classical approach for long times propagation in quantum systems. Essentially, the system need to be strongly chaotic in order to work for extremely long times. If the system does not satisfy strong chaos, perhaps it could be applied for short times. Short times means 2 or 3 Hermite times. Okay? Well, let's go with the idea of the method first. The idea of the method is, in this system is the hyperbola billiard, a strongly chaotic system. And the idea is to construct on short periodic orbits. These are the 2 short periodic orbits of the hyperbola billiard. Wave functions, which are essentially has the shape of a Gaussian beam with, of course, as it is a periodic orbit with periodic conditions. And this wave function has very nice properties because if one evaluates the energy dispersion of these wave functions, such energy dispersion scales with h bar. And so this means that they are very concentrated in the energy spectrum. In order to have some intuition, if one evaluates the energy dispersion of a wave packet, such a dispersion is scaled with the square root of h bar. So a wave packet exists in a Wheeler energy ratio. Well, the other important thing is that the evolution of these wave functions can be described at semi-classical level on the stable and unstable manifold of the periodic orbits. And this is very nice because such manifolds are Lagrangian manifolds which are invariants. And so this manifold has very interesting properties that I tried to describe during the talk. At the end, our calculation consists of the evaluation of matrix elements of the evolution operator. For instance, in the case of diagonal matrix elements, the formula consists of a sum of a homoclinic orbits of the periodic orbits. In the case of diagonal matrix elements, the formula consists of a sum of a heteroclinic orbits, and all the elements of each term are given in terms of canonical invariance. Okay. So, an important part of the talk is dedicated to describe these manifolds. I'll construct coordinates on this manifold, and in coordinates, the dynamical evolution just a classical and at semi-classical level, it's very simple. And later, I try to show you the derivation of this, the diagonal part. The other is a bit more complicated. And finally, I'll show you numerical comparison with quantum calculations. Well, this is what I said recently. The system is a hyperbola billiard, as I said before. the example is on this periodic orbit that we name gamma. And we work with a description of the dynamics on a Poincaré surface of section because the idea is much more easy on a Poincaré surface of section. And later we go to the full phase space. Okay? And the dynamics is described by a map on the Poincaré section. And this periodic orbit on the Poincaré section is given by this fixed point. We don't use exactly the Birkhoff coordinates on the hyperbola biliar because the coordinate q has an infinity, has an infinity range, and so we change q by omega, and so the Poincaré section is described by this square in coordinate omega p. Well, this is common to evaluate the monodrome mimetics of the fixed point, and from the monodrome mimetics, one obtains the stable and unstable directions, the eigenvectors of the monodrome mimetics. The eigenvalue of the unstable direction is capital gamma, is around -6, is the expansion. We normalize this vector in such a way that the symplectic area is 1. In this case, as we have changed the q by omega, the symplectic area geometrically is the area of the parallelogram multiplied by the derivative of q with respect to omega. Well, the unstable manifold is the red curve is tangent to the unstable vector at the fixed point. So close to the fixed point, we can take points on in the direction of the unstable direction, and it's very close to the manifold. Suppose we take this point, which is a displacement epsilon in the unstable direction. Okay? We will associate a coordinate u to this curve in such a way that this point has coordinate u equal to epsilon. And the evolution of this point is this one, has coordinate epsilon multiplied by the expansion, by capital gamma, and so on. In this way, we define a coordinate on the unstable manifold. And we do the same on the stable manifold by evolving backward in time. Okay. Well, the unstable manifold is, well, the two manifolds in this system are discontinuous because here I show you a tangency, the trajectory that finishes at point B of this curve is tangent at this point, and so, sorry. And so, the curve has a discontinuity. But anyway, we follow here up to the first homoclinic point. This point are characterized, according to our definition, by the coordinate along the unstable manifold U and the coordinate along the stable manifold S. Moreover, as this curve is parameterized by a coordinate, the derivative with respect to the coordinate is a vector, is the velocity vector tangent to the curve. At this point, we have the vector tangent to the unstable manifold, and this is the vector tangent to the stable manifold. So now we are in condition to calculate two quantities associated to this homoclinic point. One is the relevance that we use in our formula, and the relevance is essentially the product, the absolute value of the product of the two distances. One is the distance from the homoclinic point to the fixed point along the unstable manifold, and the other is the distance from the homoclinic point to the fixed point along the stable manifold. This is the relevance. And the other is the Lasutkin invariant. That is the symplectic area of these two vectors. Okay. Of course, a homoclinic orbit consists of an infinite sequence of points on this plane, and it's easy to verify that this quantity has exactly the same value on all the points of the homoclinic orbits. Another invariance we will use is the homoclinic action, and this is an infinite sum over terms which are essentially the difference between the action for going from one point to the next point of the homoclinic sequence minus the action of the periodic orbit. This infinite sum converges because this term goes exponentially to 0 as we reach the fixed point. Well, an equivalent definition can be used for the homoclinic Maslov index. It's an infinite sum in the same way. Okay. Here I've shown you several the unstable manifold for longer times. The stable manifold is symmetric. It's in this direction. Well, and now I try to show you that by using a dynamical coordinate system, the equations of motion can be written in a very simple way. What it means this way, that the equations of motion have no chaos. Which one is the idea? Okay, we have here the fixed point, and we define with a boundary the black curve, a region in the neighborhood of the fixed point, and such a neighbor define a piece of the unstable manifold, which is the red curve. The red curve is the manifold up to here, up to the boundary. And the same for the stable manifold. The stable manifold is reduced to this piece. Up to the boundary we use. Then, by using the other manifolds, longer manifold, we can define the coordinate of a point A simply by moving along the stable manifold up to reach the curve, the red curve. And here we have the coordinate U. And we move along this unstable manifold up to reach the curve, the blue curve, and we obtain the coordinate S. Of course, this definition only works for homoclinic points. Nevertheless, homoclinic points cover densely the plane. So it's a good definition. Now, for instance, well, these coordinates are US equal to USA, but now I say you, and B is a coordinate with the coordinate U equal to 0, because B is on the blue curve. The point is that A, the evolution of A by the map is the point B. Now, so from this we don't obtain this evolution. But if we say, well, we use this coordinate system for the step 0. The dynamics on the map is by steps. And for step 1, we don't use this boundary and this curve. We use the evolution of such a curve after the first by the map. So the boundary, this boundary is this one. The red curve increases because it's expanded, and the blue curve is reduced here. So if we observe now the coordinates of the point B, now the coordinates of the point B, that is UB and SB, are related to the coordinates of the point A simply by multiplying, in the case of U, by gamma, and in the case of S, dividing by gamma. And this is general, forward or backward. So the equations of motions reduce to these expressions by using a dynamical coordinate system. Of course, if we observe the second step, we immediately notice that this coordinate system is nice in order to describe WKB states, which are localized on manifolds. Well, now we try, we try to generalize this point to the full phase space. And the idea is that one point on the point-carried section is generalized by a closed curve on the full point-carried, on the full phase space. And now we will define a closed curve. A closed curve is constructed in a simple way by using a fixed point on the periodic orbit, an arbitrary point. We take the unstable manifold as such a point, and then by using this recipe, we are able to construct a closed curve near the periodic orbit, and the point is that this closed path is on the unstable manifold. By evolving such a closed curve, we obtain closed curve far away from the periodic orbit. Here I use the full hyperbola billiard, not just the symmetrized one, in order to show clearly these figures. The previous periodic orbit is now this one. And here I show you the closest path as we move away from the, here continues, and here continues, and this is the last one, as we move away from the periodic orbit. So, by using this coordinate system that describe the motion in the transverse direction to the periodic orbit, and a coordinate system describing the motion along the closed path, we are able to describe the unstable manifold in a simple way. For instance, if you notice here, the evolution of a point on the unstable manifold in terms terms of these coordinates. And here I include tau in place of t, because this tau is periodic. It's equal to t as the modulus p of tau is t. Then this periodic coordinates evolve by the fluke according to a uniform motion. Very simple. And the chord transfer coordinates u evolve according to a hyperbolic motion. Okay. Here I show you, in order to have some notation, a grid in this coordinate system is observed on the Euclidean plane. We project the unstable manifold on the Euclidean plane, and we obtain this, which is essentially is a piece of a tube. As this is another grid. And here, the lines, the vertical lines, correspond to this line. These vertical lines provide the generalization of the previous vectors on the curve, because we take the derivative with respect to u. And this provides the generalization of the previous vector. And then with this vector and our definition of coordinate u and s equivalent on the stable manifold, we generalize the relevance and the Lassutkine. Now, a point of a homoclinic point is characterized on the unstable manifold by coordinates tau and u, and on the stable manifold by the coordinates tau prime and s. Of course, we do all the calculations on the Poincare section, but these quantities are related in a simple way to the previous quantities. And we can do also, we can define a dynamical coordinate system, but in this case, this dynamical coordinate system changes continuously with time. So we define dynamical coordinates u and s in the neighborhood of the periodic orbit. We take a tube in the neighborhood of the periodic orbit, and in such a tube we define all the coordinates according to such a dynamical coordinate system, and the equations of motion have no chaos again, and so the Hamiltonian defining such equations of motion without chaos is simple, is this one. Here we change tau by theta, is tau divided by the period p, because in general the period of a periodic orbit changes with energy, but it's essentially the same. So the Hamiltonian in full phase space is described by the angle action variable theta phi defining the uniform motion, and the variables us defining the pure hyperbolic motion. This is for the Hamiltonian, used for a forward evolution, and for a backward evolution, we use in place of theta the variable theta prime, which is tau prime divided p. Tau prime is the variable, the periodic orbit along the closed path on the stable manifold. Well, now we are in condition to evaluate the quantum state I had shown previously, and to evolve such a quantum state on the manifold. This is, I repeat, this quantum state has the shape of a Gaussian beam with periodic condition, as such a conditions are satisfied and discrete values of the mean energy will satisfy a Bohr-Sommerfeld rule. Well, the properties that the energy dispersion is scaled with h bar. And now we construct this state, which is essentially a local plane wave along the periodic orbit and a transfer wave packet with minimal uncertainty, but not in this configuration space, but we use as configuration space theta and u, the coordinates on the unstable manifold. And this, in this coordinate system, this is our configuration space now, the description of this state is trivial. It's a plane wave along theta and a wave packet with minimum uncertainty. Okay? The evolution of this wave in these coordinates are described by the quantization of the previous trivial Hamiltonian. Is this one? And so the evolution in time of this state is the evolution of a wave packet. Well, we can do exactly the same for a backward evolution. This state is now a WKB state on the unstable manifold, and this state is a WKB state on the stable manifold. And now we try to evaluate the contribution of a homoclinic orbit to the autocorrelation of these wave functions. The idea is, well, here we have the autocorrelation, and then we write such autocorrelation as a ket, which is the forward evolution, a forward evolution of the ket for a half time, and this is the backward evolution of the bra for a half time. Then here we have the WKB state on the stable manifold, and here we have the WKB state on the unstable manifold at semi-classical level. In order to find this overlap, then, at semi-classical level, one has to find the intersection of the stable and unstable manifold. Such an intersection consists of the periodic orbit itself and the set of homoclinic orbits. Well, here I try to describe the contribution of one homoclinic orbit. One homoclinic orbit is parameterized with a coordinate 5 between minus infinity and infinity. And this parametrization on the unstable manifold is given by this description, and on the stable manifold is given by this description. Now, at a given value of 5, we have the unstable manifold is a curve like before on the Poincare section, and the stable manifold is another curve. Here we have a problem because this coordinate is defined at time t, at positive time, t over 2. And these coordinates are defined at time minus t over 2. And the coordinates depends on time. So they are different coordinates. So we will evaluate this quantity for a given value of 5 at positive time. And in order to obtain the relation between this amplitude in terms of the coordinate s defined at minus time and the coordinate s prime defined at positive time, we use simply that the probability density is the same, and then from this we obtain this expression in order to relate the amplitudes. So for a given 5, the contribution is given by this expression at semi-classical level. the next step is to integrate over 5 between minus infinity and infinity. This task is not very complicated because, for instance, the denominator is the Lasutkin, which is invariant, and we can, without problem, we eliminate this from the integration. And we replace the previous expressions of the WKB state and replace them. And finally, we obtain this integral. And this integral has an explicit solution in terms of the modified Bessel function of 0th order. In order to provide a simplest interpretation of the result, we define the turn-on time. This time is the time when the periodic, the homoclinic orbit start to be relevant. This is a function that later I'll show you this in the next transparency. So at the end, the contribution of a homoclinic orbit is provided by this expression. Later, we'll replace these are the phases, the phase of the homoclinic contribution in the coordinates on the stable and unstable manifold. We replace by this phase by the homoclinic action and the homoclinic mass of index, where it's easy to evaluate this. Okay. The function f I mentioned previously is this one, and this is the form. It's a function that decreases very quickly for negative values of the argument, is the exponential of an exponential, and decay exponentially for positive values of the argument. Here, I show you the autocorrelation of this resonance. I named resonance to these wave functions at quantum level as a function of time, but here in place of using directly time, we use a length. This is the time multiplied by the classical velocity at the mean energy of the wave. We use a length because in this system, the topological entropy that describes the increase of classical objects is constant, is this number, is constant in units of 1 over length. So, if we use this quantity, this length, the exponential of this quantity multiplied by the topological entropy provides is proportional to the number of homoclinic orbits we need in order to evaluate the autocorrelation. Okay. Well, the decay for short time is provided by this function. This is the autocorrelation of a wave packet. And it's interesting to compare with the autocorrelation of a wave packet launched along the periodic orbit. This is a typical autocorrelation studied by Professor Heller. And we notice that the frequency of this autocorrelation is much greater than this one. As a function of h bar, this frequency increases with as 1 over the square root of h bar. So this autocorrelation is more and more complicated as we go to the semi-classical limit. In play, in this case, for these wave functions, the autocorrelation is independent of h bar. So the frequency is the same, essentially the same in the semi-classical limit. I'm sorry. Here, as the first part, for short time practically equal, we take the quantum calculation minus the semi-classical short time calculation, and we compare this with the homoclinic contribution. And here is a comparison. In red, we have the first term, the first member, and the other is the sum of homoclinic contribution for different numbers of contributions. Up to 2 times the Hellenfest time, practically it's unnecessary to include homoclinic orbits. Later, we need to include homoclinic orbit. This curve corresponds to 10 contributions. Up to here works good. Later, we need to include more homoclinic orbits. This curve continue, this blue curve continue to here, include 1,000 contributions. And then we need to include more orbits because this time is very large. This time corresponds to 13 times the Hellenfest time. We include more contributions. Up to here, we have included 100,000 contributions. And finally, this curve shown here includes 8 million contributions. So evidently it works very nice, and this is the imaginary part also. But now let's go to study the errors of this semi-classical approximation. Here we show others, resonances with other numbers of excitations. And in some cases, we observe a discrepancy that is greater than in other places. It's clear that if we observe this curve, we notice that they are practically random. It's not, there is no system active between one and the other, because really we are considering very long times. Well, now we will evaluate the error of the semi-classical calculation. And here we have in red, we have the difference between the quantum and semi-classical calculation for the real part, and in blue, the difference between the quantum and semi-classical calculation for the imaginary part. As we notice, this is increased slowly, but here appear increased anomalous. There is an anomalous error. In order to have some idea of the error, of the semi-classical error, we compute the quantum calculation for the non-relativistic Hamiltonian and for the relativistic Hamiltonian. Because at classical level, the formula, the semi-classical formula, is exactly the same for the two Hamiltonians. So a lower bound for the error should be given by the discrepancy between the quantum correlation of the non-relativistic case and the relativistic case. Such a difference is shown here. So we expect that the best situation should be an error of this type. And we notice that here the error is more or less this one, but appear an increase at this time. And this is related to diffraction. Here I show you the first forbidden homoclinic orbit of this system. This orbit is not included in the calculation because here this piece of trajectory goes through the hyperbola. Okay? So if we evaluate the time when these homoclinic orbits start to be relevant, we obtain this. So this is a clear indication, yes, fine. Yes, thank you, that the increase of error is associated to diffraction. So in order to improve the calculation, we need to include diffraction corrections. I try to describe very quickly some aspect of the off-diagonal matrix element, perhaps. The function that appear in the case of off-diagonal matrix element, it depends now of two parameters, two dimensionless parameters. Remember that in the previous case, the function, is this one. Well, now it depends on two parameters. These parameters, one is epsilon. This parameter describes the difference of stability indices between the periodic orbit of gamma and the periodic orbit delta. And the other parameter, eta, is describe the difference of energy, mean energy, between these two waves. In such a case, this function is a bit more complicated, but we can expand such a function in terms of expansion in terms of epsilon, around epsilon 0. The first term of such expansion is a function like in the homoclinic case, but now the order of the modified Bessel function is not just 0, but is pure imaginary and has value the parameter eta. Eta is a measure of the distance in the spectrum of the two wave functions. As eta increases, the two wave functions in the spectrum move away, and so the correlation decreases. Here I show you some examples, some comparisons between the quantum and semiclassical for 1,000 of a bit more heteroclinic orbits. The comparison is very nice, but of course for a short time, because the number of heteroclinic orbits is not a million. And here, eta increases, and of course, the correlation, the amplitude of the correlation decreases, here too. And here I show you a case where eta is very large, and the amplitude of the correlation is extremely small, even though in this case, you observe a very nice comparison between quantum and semiclassic. So this formula works very nice even when the two wave functions are far away in the spectrum. So, conclusions. Working in strongly chaotic system with 2 degrees of freedom, we find matrix elements of the evolution operator between wave functions highly localized in energy. These matrix elements are written in terms of canonical invariance of homoclinic and heteroclinic orbits. These matrix elements are explicit function of time, and this is nice because it's possible to evaluate its Fourier transform explicitly, and such a Fourier transform is a function of the energy. And as a function of the energy, provide information about the structure of eigenfunctions of the system. The extension of these formulas to more degrees of freedom should be, in principle, straightforward, I believe. And it would be interesting to verify this formula in open system, because this formula applies to closed system or an open system too. For instance, the 3-disk. Finally, the extension of these formulas to systems with traces of integrability is an open question, at least for me. Thank you very much.